Okay, so we're in chapter 13. Last week you learned about flux, section 13.6. So with flux, what we're doing is we have a vector field in three-dimensional space, and we have a surface in three-dimensional space. And we want to know if the vector field, which could be like a velocity field, if that vector field is the rate of flow of the vector field, is it overall outward from the surface or inward from the surface? And a value of that rate of flow, that net rate of flow, is called a flux value. And we learned how to do that in section 13.6 last week. Now, also another application in chapter 13 that we've learned about is, you have a force field in either two or three-dimensional space, and you want to know what work the force field does in moving a particle from one point to another point in two or three-dimensional space. So we actually learned that, hold on here, we actually learned that computing the work is equivalent to computing the sum of line integrals. And if we have a closed path in two-dimensional space, you can compute the work that the particle does in moving, that the force field does in moving that particle once along that closed path using a special theorem. What special theorem is that? Do you remember? What special theorem can be used when you have a positively oriented, simple closed curve in a plane that encloses a region in two-dimensional space in the XY plane, and you want to compute the work that the force field does in moving the particle once along that closed path? What special theorem is used to find that work? Do you remember? From section 13.4, it begins with a G. That's right, Diodath, Green's theorem. Green's theorem. So Green's theorem is great because it can be used for that kind of application. And remember, vector fields are not always conservative, right? So we need theorems that'll help us out for just sort of general vector fields. But the thing about Green's theorem, yes, Green's theorem allows us, given a vector field, it allows us to find the work that the vector field does in moving the particle once around this closed path. But we're limited to two-dimensional space, to the XY plane. What if your particle, it moves, does a closed path, but it's in three-dimensional space? Okay, what do we do then? You can't use Green's theorem because Green's theorem only applies to vector fields in two-dimensional space. Okay, so the situation is we want to be able to compute the work that a force field does in moving a particle once around a closed path in three-dimensional space. So given that situation, okay, we have here in Figure 1 sort of a picture of that. Okay, and actually they mentioned right here in the beginning. Okay, they mentioned right here in the beginning. Okay, I'll highlight it because it's nice to have that there. Stokes' theorem, it can be regarded as a higher dimensional version of Green's theorem, where Green's theorem relates a double integral over a plane region D. Okay, Stokes' theorem relates, Green's theorem relates a double integral over a plane region D to a line integral around its plane boundary curve. But Stokes' theorem relates a surface integral over a surface S to a line integral around the boundary curve of S. So let's see, let's try to make sense of this. So here's a situation, okay, where you have a you have a person, they're showing a human, it looks like a human being there, right? Walking along some path in three-dimensional space, some closed path in three-dimensional space. And there's what's called positive orientation. So if you walk in the positive direction around that contour C, around that curve C, with your head pointing in the direction of the normal vector is pointing upward, out from that. So what I want to say is the curve C encloses a surface. You see that? That curve C in figure 1 encloses a surface. The curve C is think of it's like the rim of the surface. It's like the rim of the surface. Okay. Think of a balloon. A balloon is the surface of a balloon, but the rim of that surface is the part where you blow up the balloon. That's like your rim. Okay. Well, that curve C is like the rim of the surface. And positive orientation means is that if you walk in the positive direction, okay, around the curve C with your head pointing in the direction of the normal vector, the surface will always be on the left. Okay, that stands for positive orientation. Okay, are there any questions so far? Okay, well let's continue on. So what Stokes' theorem says is the following. What Stokes' theorem says is the following. Hold on here. If you have a piecewise smooth surface that's bounded by a simple closed curve with positive orientation, and you have this vector field, okay, you have this vector field, hold on, let's make it show here. Yeah, you have this vector field F, okay, whose components have continuous partial derivatives over the three-dimensional space. Then the work that the force field does in helping the particle move once around that closed curve is equal to the double integral of the curl of F dot ds. Okay, the curl of F dot ds, the ds vector. So do you see here in this Stokes theorem on the left, that integral stands for, that stands for work, find the work. But the integral on the right, or the double integral on the right, what does that represent, the double integral on the right? What kind of integral is that? The curl of F dot ds vector. I mean, you're computing what on the right? Ah, good, Robin. You're computing flux. You're computing flux. So everything you learned about computing flux from section 13.6 applies here in Stokes' theorem, except that your vector field is going to be the curl of your vector field. That's your vector field that you're going to be working with. Okay, and this is called Stokes' theorem. Okay, and they give a proof of it, a special case, but it's not a general proof. I want you to just take it on faith right now, this Stokes' theorem. They have a footnote here about the gentleman who invented it. Let me see here. They usually have a footnote somewhere. Let me see if I can find it here. Well, they mentioned that it was named after mathematical physicist Sir George Stokes. How many have heard of Stokes, maybe from a physics class? Heard of that name? He lived from 1819 to 1903. I don't know if that's familiar to any of you, but Stokes was a professor at Cambridge, and he was noted for his studies of fluid flow and light. Okay, and that's one of the people associated with this theorem. So all we need to do, well, hold on, let me show the theorem here. Yeah, I'd like to just look at some examples here. I'd like to look at some examples. Are there any questions here before we move forward? Okay, then let's go ahead. Let's go ahead here. One moment. Let's go to hold on. This example here. Okay, they talk about using Stokes' theorem to compute a line integral. Okay, well, remember, well, yeah. So let me just show you how this works. So here's your vector field, which equals negative y squared I plus xj plus z squared times k. And c is the curve of the plane. It's the curve of the intersection of a plane and a cylinder. Okay, so first thing you want to do to use Stokes' theorem, well, remember, you're going to use Stokes' theorem to compute that line integral, but really you're computing the work. You're computing the work that the force field does in moving a particle once around this curve C, which is the intersection of a plane and a cylinder. So you find the curl of that vector field F. Okay, and you know how to find the curl. You know how to find the curl of a vector field. Okay, and the curl of a vector field, of this vector field, happens to be equal to 1 plus 2y times the vector k. And in the picture here, okay, you have here in figure 3 a picture of the intersection between that cylinder with radius 1 and the plane y plus c equals 2. So there is the intersection, and you have a curve C that is the intersection between that plane and the cylinder. Okay, and then inside the curve C, there's a surface. There's a surface. Okay, and well, first of all, are there any questions? Are there any questions so far on this? Okay, so what we want to do is we want to compute the work. We want to compute the work that this force field does in moving a particle once around that closed curve C. Okay, so in this case, all right, the surface S, okay, can be written as a function of x and y. Okay, so I'm going to show you how to do this problem the one way, okay, and then try to show you later on another way. But let's do it the way the book does it, okay, for now. So Z, the surface S, well, what is the surface S? Is the surface S there that's highlighted in blue? Is that the cylinder or is that the plane? The surface S enclosed by that curve C. It's the plane. That's right, Diodath. That's right, Robin. It's the plane. And the plane is z equals 2 minus y. So if you were, well, are there any questions on that? All right. Well, if you then, hold on here. One moment. So what they're doing is they're using equation 13.6.10 to do this, because you can write the surface as a graph of x and y. Again, I normally like finding the parameterization of the plane and working with just one formula, but I just for good measure want to show you this way as well. I'm going to click on that equation. Okay. Let's see. I clicked on, let me see, I clicked on something here. Yeah. So hopefully you can see it. So when z is a function of x and y, the flux can be computed as the double integral over the region D with that integrand. How many have used, hold on, I got it, it's getting cut off a little bit. Hold on, one moment. I won't. All right, we'll just have to let it kind of as is, but that's fine. How many have used this formula for computing flux, like from section 13.6, when z was a function of x and y? How many have utilized this type formula, formula 10? Okay, Robin has. All right. All right. Well, and maybe, the other way is to just use and Ryan has. Okay. So maybe, the other way is just to use the original, the parameterization of that plane. But, this is the formula here that you can use. So in this formula, and I'm just making a note of it right here. Okay, so the P and the Q and the R, the P and the Q and the R in the formula. Do the P and the Q and the R come from the vector field, or do they come from the curl of the vector field, the P, the Q, and the R? Can you tell me? Well, they would actually come, Ryan, if we're going to use Stokes' theorem, we have to use the curl. We have to use the curl of the vector field. Okay, so actually, let me just see here. One moment, class, one moment. I'm just looking at one thing here. One moment. Because I notice in the solution they are leaving out a few details, and I'd like to fill those in for you. Okay, I'd like to fill those in. Hold on. Okay. Let me go to the whiteboard here. Let me go to the whiteboard. And write down a few things here. So again, we're looking at example 1, section 13.7. Feel free to have your ebook open to that. All right, and in this example, section 13.7, example 1, okay, the curl of the vector field is equal to 0 I plus 0 j plus 1 plus 2y times k. So P is equal to 0, Q is equal to 0, and R is equal to 1 plus 2y. Now, using and also let me make a comment here. G of xy is equal to 2 minus y. Okay, that's that plane. The partial of g with respect to x will equal 0. The partial of g with respect to y will equal -1. Okay? Now, using that special formula, because the surface can be written as a function of x and y, special formula says compute the flux integral using this formula. Only because g is a function of x and y. Okay. Well, negative p is the same as -0. So you have -0 times the partial derivative of g with respect to x, which is 0. Minus q, well, for the curl of f, see, it's the curl of the vector field that students always make this mistake. They work with the vector field instead of the curl of the vector field when they apply Stokes' theorem. The q is equal to 0. The partial of g with respect to y is -1. And then r is 1 plus 2y. Okay, so this here in example 1, well, all this here just equals 1 plus 2y. And you notice I haven't committed yet. I haven't committed yet to, it's a double integral. So I can either use polar coordinates or rectangular coordinates to compute that double integral. But I don't want to do too much at once. So, I stop there. And now what I want to do is go back to the book. But are there any questions on what I wrote here for example 1? I'm just really filling in the missing pieces. okay, in their solution. Okay, well, if you're good, then let's go back to the ebook. Okay, so here then, they get, hold on. There's the double integral of 1 plus 2y dA. And it looks like they're going to use polar coordinates. They're going to use polar coordinates to compute this flux. Why use polar coordinates? Well, what would region D be? What would region D be? Well, if we look in figure 3, if you take the surface S and project it down into the XY plane, you get a circle. Okay, you get a circle with radius 1. Right? And so polar coordinates is the way to go. And so you're going to get then, when you work this double integral out, you're going to get pi. Okay, you're going to get value pi. And pi is equal then to the work. It is the work that this force field, that the force field does, not the curl. Pi is equal to the work that the force field F does in moving that particle once around that path. And I guess the force field is helping the particle move along that path, that curve C. That's, you know, that curve there. I guess the force field's helping the particle move along that path with that orientation. You know, you see the arrow on the curve there. It's going in that direction, positive orientation. I guess it's helping it because the work is positive. Okay, and that's how Stokes' theorem is done. And you see, you need to use Stokes' theorem to compute the work when you have a curve, a closed curve in three-dimensional space. Okay. Now let me ask you this: if the vector field F were a conservative vector field, what would the work be? What would the work be in this problem if the vector field F were a conservative vector field? What would the work be that the vector field does in moving the particle once around that closed path C? Good, Christopher. Good, Ryan. The work would be 0. But of course, conservative vector fields, although they're you know, we live in one, the gravitational field, and you have, you know, electrical fields and so forth, but there are plenty of vector fields that aren't conservative. And, you know, that's why Stokes came up with this theorem. You know, most of these theorems you're learning are because, you know, human beings wanted more knowledge. You know, they needed more knowledge to solve problems. You know, you couldn't send, you know, Elon Musk couldn't send a spaceship up into space back in the 1800s, right? But without Stokes, he probably couldn't do it, right? The point is, the technology that we have here in the 21st century is based on all these wonderful results that we've had in history, and so it's really a beautiful, beautiful thing. Are there any questions on this? Any questions on this example from Stokes' theorem? Okay, that being said, let me stop the recording.